Good evening. Welcome to the U.S. Geological Survey and another installment of our monthly public lecture series. My name is Leslie Gordon, and it is usually my pleasure to introduce the lectures each month. Before I introduce tonight's speaker, I do have some announcements. We always want you to come back next month. We have a great talk scheduled by Dr. John Keeley. He is actually stationed in our Sequoia Kings Canyon field office, so he'll be traveling to Menlo Park, and he's going to be talking about fire-climate relationships in the Sierra Nevada. There's a big caveat to this. Perhaps you've read in the news that there is a possibility of a government shutdown on October 1st. So here's the deal. If we're shut down, we can't have a public lecture. If we're shut down and we're still shut by October 19th, that's going to be our cutoff day, 19, then we will not have this public lecture. Now, those are a couple of very big ifs. If we shut down and if it continues till the 19th. And I would say in that case, please just follow your local news reports. You'll know as much as we know. So I just have to make that caveat, but we have planned a public lecture for October. The lecture itself will be on the 22nd. All right. And I've also been, oops, I touched something. Thank you. Sorry. I fixed it. If you can, we always have a question and answer session after the talk, and if you can save your questions to the end, we would really appreciate that. So we'll deal with that later. But now it is my great pleasure to introduce Curt Storlazzi. Dr. Storlazzi is a research oceanographer, and he is our chief scientist for the USGS Pacific Coral Reef Project and the USGS sea level rise and climate change impacts to U.S. Department of Defense facilities on Pacific atolls. Did you get that? Curt actively conducts geologic and oceanographic research on coasts and continental margins in the U.S., specializing in coastal hydrodynamics and sediment transport. So it is my pleasure to introduce Curt Storlazzi, who will speak about coral reefs, climate change, and atoll sustainability.
Thanks, Les. So if this is like most of our public lectures, there's probably a lot of folks in this room that know a lot more about me, about a few of the things I'm going to talk about tonight. And a lot of you folks probably got to work on some incredible projects at Lockheed Martin, TRW, all these things in defense, or maybe in places like NASA, and you got to work on these incredible teams and doing very important research for our nation. And I don't know if I could say the need for this research is as high as some of those great old programs, but I will say this is the research I'm presenting tonight is part of is work done by a large team of absolutely wonderful people, some of the tops in their fields, and so the credit goes to all of them and not just me. So background, what is an atoll? An atoll is a very low-lying islands built upon reefs with a large central lagoon. This shows Palmyra in the Central Pacific. Here's a satellite view of another one again. So very low-lying, few islands scattered upon a large reef platform. And so again, those are built by carbonate secreting corals, and I guess I could say that there's a lot worse places in the world to work. So in the Pacific, in our area of operations, there's a number of atolls, including the majority of the northwestern Hawaiian Islands, all of the U.S. Pacific remote atolls you see here that, thank you, were just made a large marine protected areas. Most of the Marshall Islands and most of the eastern two-thirds of the Federated States of Micronesia. There's also a number of other ones, the Gilbert Islands and others. The northwestern Hawaiian Islands, the Pacific Remote Islands are direct U.S. assets. The Marshall Islands and the Federated States of Micronesia fall under the Compact of Freely Associated States. Most of you know that these were old World War II battlefields where Nimitz pushed up through most of the Central Pacific. We now have defense compacts with them. We provide a lot of services for them, and most of that's through the U.S. Department of the Interior's Office of Insular Affairs. As you know, we at the USGS are the geoscience wing for the Department of the Interior. Now, if you take just the U.S. ones, the northwestern Hawaiian Islands and the Pacific remote atolls here, which are basically most of these blobs, you'll notice that this is a map of U.S. exclusive economic zone. You'll notice that just these atolls alone comprise as much U.S. exclusive economic zone as the U.S. East and Gulf coasts. So why is that important? Well, if you like to eat tuna here in the U.S., most of your tuna comes from that. And a lot of large fisheries are out there. But what's becoming more important, and you probably heard about in the news, my good colleague Jim Hine is one of the world experts on it, is there's a lot of deep sea minerals out there. And so a lot of these really weird sulfate, sulfide crusts and iron manganese nodules and iron manganese crust has a lot of these really weird little parts of the periodic table that you probably don't think about, but there's like 1 picogram of it in like every cell phone ever made. And a lot of these are very rare. You can't find them on the continental U.S. And there's a big push for, obviously, the U.S. law of the sea to secure those mineral rights for the future. The other thing is they're very important for Department of Defense. Here shows Wake Island, which is part of the Ronald Reagan Ballistic Missile Test Facility. Kwajalein, which is in the Marshall Islands. So it's kind of like Cuba. We don't own it, but we got a base there. And that's U.S., except, yeah, some of the other parts of Guantanamo Bay. We separate that. It's U.S. Army Garrison Kwajalein Atoll. Johnston was part of a large U.S. Air Force facility until about the past decade. But this is where we do a lot of our anti-missile, anti-ballistic missile testing facilities. It's where we've got our primary deep space tracking radars, a lot of radar development, the new space fence, $860 million anti-ballistic missile test facilities being built there right now. And Johnson is actually where we did, at the end of the Cold War, we decommissioned most of our biological and chemical warfare. Here shows just a little bit of Agent Orange that was set up for decommissioning. The other thing you might know is a lot of these places in the Marshall Islands, like Eniwetok and Bikini, was where we detonated over 300 atomic weapons. A lot of that sprayed a lot of radioactive material all over. Actually, bless you. There was 2 sites here in Runit on Eniwetok where they basically collected all this really highly radioactive material, including plutonium, which has a half-life of 20,000 years or so, and dumped it in there. And here you see that nice concrete cap now, barely above sea level. On Johnson Atoll, they were doing high-altitude atmospheric tests. This shows the bluegill pine test, which was a 10-megaton, I believe, warhead that blew up on the pad, spread plutonium all over the place, and they bulldozed it up into this, whoa, where's my cursor, up into this northwest corner here. And as you can see today, there's a nice little 3-foot wall separating that from the sea. Now, so not only is there Defense Department, there's legacy radionuclides, but there's also a lot of people packed into a very small space. This shows Delap, the main island on Majuro. There's about 25,000 people here. Ebi here on Kwajalein Atoll. This is the highest density island in the world. It surpasses Malé and the Maldives. There's 30,000 people here. This is about 2 miles long and a couple hundred meters wide. And just to show you what these places look like, this is from the sea. This is about a mid-tide, no big storm. Look how close those islands are to, or I mean, those houses are to the water. Here shows the main government building. There's at least 6 foot of riprap between the ocean and it. Here's the major fuel facility and power generation site. Again, at least here they've got 6 foot of rock. Here's the runway, and yes, that's actually seawater that just comes up during high tides. Not storms, just high tides. And so this is the main air link for all of these people out. Okay, so what is an atoll? Well, atolls are really fascinating kind of formations. You have and they're really kind of poorly understood. They've got this very low topography. They're maybe at most 2 to 3 meters, 6 to 10 feet above sea level. They have very, very steep bathymetry. These slopes are often greater than 1 to 1. I'll show you a picture where off Kwajalein, it drops off at about an 80-degree slope from about 100-foot water depth down to 10,000 feet. They've got a very limited freshwater lens. So what happens is when rain falls on the island, it actually pushes the salt water away that sits under the island, and there's this freshwater lens. And that, whoa, sorry, I don't know how that happened. And that freshwater actually floats on the salt water because it's less dense. It's also kind of interesting because you've got unconsolidated or loose sand and gravel on most of the active island, but then it sits on this carbonate or reef platform here. So instead of it being like a Gulf Coast beach where everything's just sand, you've got sand and rock together. And you technically have a changing biogeomorphic system. What I mean by that is there's active coral growth and development in certain places. So how do they form? Well, Darwin in 1839, really brilliant, made this kind of figured out in his head this model by going around the Pacific. And it's basically you have a volcanic island that starts to have reefs form around the edges. Now, as that island cools and the continental or the tectonic plate it's on starts to sink, those reefs still grow up as it starts to sink. And so then you go from these fringing reefs to now a barrier reef with a lagoon. This island continues to sink as the plate cools more and more and more. Now all of a sudden the island's completely underwater, and now you have just this carbonate ring with some islets on it. Now, I grew up on the East Coast where I always thought of sea level, 20,000 years ago was about 300 feet, 360 feet lower from now, and it just kind of slowly came up. Well, what we found out recently, one of my colleagues, Eric Grossman, and a buddy of mine, Chip Fletcher at University of Hawaii, showed is that actually in the Pacific, because of when all these big glaciers melted off the land, it actually affected the Earth's mantle, and there was these weird readjustments. But actually, sea level didn't just come up from 360 feet below up to present, but it actually overshot. And it actually, sea level was about 1 to 3 meters higher than present about 5,000 to about 2,000 years ago. And what was interesting is during that time, this shows an example of, so there was these old carbonate islands that when sea level rose, all of a sudden waves could break up those corals and pile all that coral rubble up in sand, and that's when most of these islands formed, was during the sea level high stand about 5,000 to 3,000 years ago. And so they formed during this period of higher sea level. Sea level has now dropped back down to this present, and I'll show you the trajectory for the future. So this just shows, please don't worry about too much, but this just shows maps of, there's a lot of dots in here showing different island groups. Basically, that sea level high stand wasn't uniform across the Pacific. It was higher in some areas than others. So in places like the Marshall Islands, where we're focusing, it was about 2.5 meters above present. In the Carolines, it was a little lower, about 1 meter. Kiribati, which is like Tarawa, and the Gilbert's a little lower, but it wasn't uniform. That's all you need to know. And so a gentleman, Mark Dixon, in the mid-2000s, went around to all these different island groups and figured out how high was sea level during that high stand in these different island groups, and when that ended, when sea level got back to the present. Well, if you take this number and the termination date, don't worry about all the specific numbers, and the tidal range, so when did sea level get back to present was about anywhere from 500 to 900 years ago, And then what he's saying is, well, if sea level starts to rise again, which it is, when is that mean tide level going to reattain that previous tide level? So basically that crossover day is when in the future the high tides will approach those levels that occurred during the high stand. Why there's two different numbers is whether we're hitting 3 feet above sea level by the end of the century, or 1 meter, or if it's a half a meter. So if sea level rises at a slow rate, it may come up, we may not hit it till about 2100, 2150. If it comes up faster, maybe we're going to hit it from 2050 to 2070. So again, this is when limited inundation, the tides are going to flood a little bit of the islands every day. That's scary because, I mean, knock on wood, I'm going to be alive to see that. However, we know sea levels rising in the Western Pacific at 2 to 3 times the global average. So it's gone up 1/3 of a meter, or almost a foot, in the past 20 years alone. And you see these highest rates of basically 10 millimeters or centimeter per year is in that area where most of those atolls. The 2012 U.S. National Climate Assessment, or we can go to the Intergovernmental Panel Climate Change AR5 report, and they're providing a bunch of sea level scenarios. Basically 0.2 meters by 2100, that's probably not happening. That's assuming no climate change. Highs up to about 6 feet. We're actually already on the trend in this direction, up to about 1.2, but kind of right now the thought's somewhere between about 0.8 and about 1.2, 1.4. However, all of these projections admit this one issue, and this is a quote directly out of the Intergovernmental Panel for Climate Change, is that we don't understand the response of ice sheets. So like the big Antarctic ice sheet that's got kilometers and kilometers of ice, what we started to see, there's been a number of publications in the past few months that are showing that these things may become ungrounded and break apart much faster than we can ever expect. Another thing you can think of is you have a big block of ice that melts relatively slowly because it's got a lot of volume to surface area. As it starts getting smaller, it's got more surface area to volume, and it starts to melt faster. So most of the cryogenic scientists, those that really study glaciers, say, folks, the models that are putting us in here don't take into account the ice melt. So I'm not saying which way it's going to go. I'm just telling you what they say. So, okay, so if we're just worried about, and I shouldn't say just worried about sea level, but if we're worried about how sea levels just bring up the mean tides, we can physically attack that problem of figuring out where those problems are relatively easy of mapping it out. Basically, we just take a digital elevation model, like a topographic model of the islands in mapping software, and basically sink it or raise the sea level, kind of like filling up water in a bathtub. Less islands exposed at higher sea level. Here's a great product generated by National Geographic, basically showing if all the ice in the world melted, what part would flood. So you have, here's your present-day shoreline, here's if sea level rose 300 feet. So we can do this really easily. Now that's all the ice. That's probably going to be sometime past 2100. But we can do the same thing. Here shows an island in the northwestern Hawaiian Islands that shows what areas will be covered at what point in time. So, you know, we have an island that you see the outline here, and as we add more water, sea level rises, less and less of the islands exposed. So we can do this relatively easy with our mapping software. However, something we need to think about is a high surf event in December 2008, which you see big waves breaking here on the reef, drove water up onto these islands. And they damaged infrastructure, ruined the freshwater supplies, destroyed agriculture in about 60% of the inhabited islands in Micronesia. Because remember, you get 1 part per 1,000 of salt water, mix it in with fresh water, and it's no longer drinkable. And so this shows on the place where we're studying, Roy Marshall Islands, this is their well fields. So rain falls on the island, sinks in that freshwater lens. Look how much salt water is sitting on top of that. So contaminated. the U.S. government actually took tankers, oil tankers, hosed them down, and had to bring out fresh water and distribute it to these islands. So, okay, the big problem is that the projected rates of sea level rise are about 2 to 10 times greater than the optimal net vertical accretion rates. So it's not that, hey, they're corals, okay, the whole island will grow as sea level rises. That's what a lot of people think. Well, actually, the rates during optimal growth, before any human impacts whatsoever, were, again, 2 to 10 times greater than those accretion rates. So sea level is going to increase over those reefs. Now, why does that matter? Well, waves in shallow water break when their height is roughly equal to the water depth. So an 8-foot wave breaks in about 8 feet of water. You can't have a 6-foot wave in a cup of coffee. So, and then run up, or is how much the water rushes up the shore face, scales with wave height. So if we have a wave height now, if we increase water depth, now that wave height is going to be bigger. There's more water, and we can have a bigger wave there. So that run-up, how much that water rushes up the beach face, is now going to be greater in the future. So sea level rise is going to allow larger waves over the reefs, higher run-up, and thus greater marine flooding and impacts. So sea level rise is going to exacerbate those hazards posed by storm waves. And again, it's not just the fresh water. Here shows maintenance shops, and I would argue that, gosh, you know, those projections before of just global sea levels going to get up in maybe 2070 to 2100 is going to be knocking at your door every day. The bigger questions is, when is this going to start happening at such frequency that we can't recover? So our objectives of this research is to provide basic understanding. These are poorly understood environments. We need to provide basic understanding of the different processes that work on there, and then very specific information to DoD itself on flooding and overwash of these atoll islands. And again, the big thing we want to do is assess the impacts on infrastructure and freshwater availability, and we're going to do it for a number of sea level rise and climate change scenarios. But the important thing is we really want to determine these tipping points. If it takes an island, say, a year to recover from an overwash event, when, because of sea level rise, will overwash start happening every year? Because then the freshwater lens will never recover. And for this example, I'm going to make this statement. Freshwater availability equals habitability. You can have an island, you don't have fresh water, you can go, what, 2 days without water? Now, okay, DoD, they can build desalination plants, things like that. You can bring in tankers maybe once a decade. But when this starts happening once a year, basically some of these islands, if this starts happening once a year, they're no longer going to be habitable. And so we're trying to figure that out. Almost like triage. You know, this is coming, we need to figure out which islands, when, and how. So, okay, so let's just do this. Let's figure out when waves are going to overwash these atoll islands. Well, there's a lot of problems with this. Basically, most of the modeling we've done in the coastal environment has been based on where a lot of the big population areas, the U.S. East and Gulf Coast, places like the Netherlands, long, linear, sandy coasts, very low gradients, all sand. Like I said here, we have this very extreme morphology, and it's really unclear if these models we've developed for these other environments can even work in these settings. Is the physics right? To be honest, they're not. They're made for very low slopes. And we have these wild slope equations in a lot of these models because it makes the models run a lot quicker. Well, we violate basically most of those assumptions in these models. And the other important thing is we don't have any field data. So we can't develop empirical relationships. And we need data to calibrate and validate models. Without data, I can make models that show purple elephants fly, right? But no, we need to calibrate and validate our models so they're as accurate as possible based on today's conditions if we're going to try to project future conditions. So the large structure of how this project is set up is we're taking some of the Intergovernmental Panel on Climate Change's AR5's global climate models. And this is all the different major countries, the Japanese, the Chinese, the Russians, the French. The US has about 7 different models. Taking all that model data, because some of them are better at some are the other, but we kind of get averages. It kind of averages out. We're using those to drive 2 things. One, on the ocean side, we run a global wave model, and then we run a shallow water wave model to figure out how much the waves are going to try to run up on the island. On the island side, in terms of the water availability, we have to have regional climate models. How much rainfall is there? How much sun? How much evaporation happens? Things like that. And then those all combine to a specific model sutra that was developed here at the USGS, which is basically a variable density flow model. Why you need variable density flow is because if you put salt water that's more dense on fresh water, it's going to kind of finger down through it, kind of like weird lava lamp. This is not my area of expertise. This is a sutra model. We've got some completely brilliant people, both in our Pacific Water Science Center and in our National Research Program that are running that. I'll show some of the results, but I'm going to speak very generally about that. Okay, so what does the future hold? What's some of our preliminary findings from our global climate modeling? So we're running the Intergovernmental Panel for Climate Change has a number of scenarios. We're going to focus on 2. One is they're called RCPs, which are representative concentration pathways. These are the same, if you know anything about the IPCC scenarios, their AR3 report, they call these scenarios SRES. 8.5 is similar to the A2 old one. RCP 4.5 is comparable to the old B1. So what these are 2 different potential emission scenarios. So this shows emissions in terms of gigatons of CO2 through time. So here's up to present, up to 2000, and we have 2. I'm going to just highlight 2. The first is 4.5. That's where emissions continue to about mid-century. Then we get our act together and we start reducing emissions. The other, 8.5, is what we call business as usual. We keep burning fossil fuels as effectively as we have in the past. And where we get the 4.5 and 8.5 is that this results in a different amount of radiative forcing, where by 2100, 4.5 watts per meter squared is generated by this emission scenario, and 8.5 watts per meter squared during the business as usual. Just for the record, at least over the past about 7 years, we've been following this pathway. So, okay, the blue, business as usual. So, okay, so Marshall Islands sit here, kind of just a larger climate thing is they're impacted by 2 different kind of main forces. One are typhoons, which generate about in that area and push in, smack the dickens out of the Philippines and Taiwan and elsewhere. These generate a lot of local storm waves, very heavy precipitation. The other are extratropical lows that come off Kamchatka and roll into the Gulf of Alaska or spin around the Southern Ocean. And we're going to break those out into 2 ways and look at both of them independently. So here shows a map. Kwajalein's out here in the Central Pacific, and the blue shows the average number of tropical storms and typhoons. And so again, like I said, they're usually a lot around the Philippines and Taiwan. You see the area out by Kwajalein is where a lot of these form. But these tropical storms dump a lot of precipitation. These red tracks show an example from 1997, which was one of the more active years. Now I'm showing you is how those are distributed now and how we think they are in the future. So now we're looking at the probability of occurrence, so high probability, and the number of tropical storms and typhoons. So the gray is the number of observations. So that's over the past 30 years. And so what we see is, on average, there's about 1.5 storms per year. So a lot of times there's no storms and then a few storms. And so what we do, these global climate models have run not only for the future, but they're run for historical time frames to see how well does the model work, right? The model can't predict the past where we have data. You sure as heck don't want to try to predict the future. But it shows here that the simulations are match the historic data quite well. So about 1.5 storms plus or minus 2 something. Our future projections under RCP 8.5 is that we're going to have a lot less. So we're going to drop from about 1.5 per year down to about 0.2 storms per year. So in this area, we're going to have fewer typhoon waves and a lot less rainfall. A lot less rainfall is critical because rainfall makes fresh water on these islands. So what about future waves? So I'm showing you here the Marshall Islands sit in this area. This is actually modeling we did of all U.S. Pacific Islands. But I'm showing you 2 different time spans, again, for RCP 8.5, so that's our business as usual scenario. So December, January, and February, this is where the big storms cross the North Pacific, like we're probably going to have this year, and smack California. Well, what it looks like is that those are going to drastically decrease. You know, the wave heights during those storms is going to decrease, and they're going to be a lot smaller. However, during the summer, that they're going to be larger than normal. These are the storms that come across the Southern Ocean. For those of you that surf or boaters or something, that's what we call the southern swell. So looks like we're going to have smaller winter waves but larger summer waves. The other thing we can do with this is we can look at the frequency of storms. So it's not just how big that punch is, but how much you're getting punched. Are you going 3 rounds with Mike Tyson or 1? What we're seeing in almost all of these simulations is decreasing frequency of storms. So again, these are the extratropical storms, and we're seeing less typhoons. So less frequent storms. Okay, so now we've got an idea of how the waves in the ocean are going to be doing. Question is now, how are they going to interact with the reef and shoreline? So one thing we do, and it's a really horrible job, they have to send people like me out and to make measurements out here to calibrate and validate our models. And this is our field area. This is Roy Namor on Kwajalein Atoll. Again, it's some of our premier space tracking radars are in these facilities here. And so we put instruments out on the reef and on the reef flat. Again, this is the edge of the reef. This is about a 45-degree slope to about 100 feet water depth, and then it's about an 85-degree slope to about a depth of about 10,000 feet. Really fascinating thing to check out. Then on the reef flat, we're also putting wave tide gauges, and we put a bunch of time-lapse camera systems that we have GPSed in so we can determine how much the waves rush up the shore face. So I want to step back real quick and talk about types of waves, because we've learned some really fascinating things about how waves interact with reefs. So if we were just to sit at one point in time and measure the height of water, we'd get something like this. This is actually data from about 34 minutes. There's waves would come by a point. Well, if we could look at kind of the waves in certain frequency bands, so those only between about 5 to 25 seconds, we'd see a bunch of waves. And that's what we typically see out on the open ocean. You stand at the edge of a pier, usually waves come by, and we call them the wave periods, about 5 to 25 seconds. However, there's also a lot of lower frequency or longer period motions. We have this thing called the infragravity band, which is about 15 to 25 seconds. And this actually very low frequency, about 20 or 250 to 1,000 seconds. Now, why it's important to study these different ones is because run-up, how much the water runs up the beach face, is 2 things. First is wave height. The other is wave period. So think about this. These wave periods here, for the exact same height, will cause, this is an order of magnitude, say 100 seconds versus 10 seconds. That means these waves will cause an order of magnitude greater run-up. These will cause even 2 orders of magnitude more run-up. So it's really important for us to understand these lower frequency or longer period waves because they cause the water to rush much more up the shore face. So here shows some data about the evolution of waves across the reef. This is real data. Don't worry about these. This axis is energy. The higher you go up on the y-axis, more energy. This is showing frequency, don't worry about these numbers, just look at these bands here. This is our incident band from 5 to 25 seconds, our infragravity band from 25 to 250 seconds, and then our low frequency. Here on the offshore, out in deep water, and up here on the fore reef, before we hit the reef crest, which is where waves break, all of our energy is primarily in that incident band. Our 10-second waves, our 15-second waves, what you usually see out on a boat. However, once we get past, when waves start to break strongly here at the reef crest, it starts to pump energy more and more into this infragravity, into these low frequency waves. And you see a good picture here that it shows this. Here's my colleague out making some measurements of the reef width. But here you see these 5 to 10-second waves out here, strong breaking at the reef crest. And then what you see are groups of waves. And then there's a lot of nothing in between. So there's these 5-second to 10-second waves, strong breaking at the reef crest, and then on the reef flat, it's pumping a lot more energy into these low-frequency waves. And that's really important because, again, these are the ones that will cause much more run-up. So what we're going to need is, if we're going to try to model inundation and flooding, wave-driven flooding in the future, is we have to do it through models. We can't make measurements. So we're using our Dutch colleagues' model X-Beach, which was developed by the U.S. Army Corps of Engineers, and our Dutch colleagues following all those big hurricanes to look at hurricane impacts in Florida. That year they got hit by 3 hurricanes in the mid-2000s. And so what you see here is just an example run. This is our reef here. You're seeing both those incident, those 5-second frequency waves, and the magenta is showing our infragravity waves. So we can model it. We're trying to model that. Don't waste too much time in this figure, but again, what's nice with the model is the X's are showing all of our data for different things like our those incident band waves, our infragravity waves, and the water levels. And we need those field data points to keep sure our model's calibrated accurately. So we can capture that, and that thus allows us to extend our data through the model. Not only can we match the waves and water levels, we can actually measure how far up the beach face it runs. So like here's our observations and our model. 98% of the waves get to this level, and the top 1% actually get up through that. So our model, with us adjusting the physics to take into account these long waves and the effects of corals, we can actually get the models to work well. So a couple years ago, my colleague Cliff Voss came here and gave one of the better talks I've ever seen about models. So a lot of times we take models and we're trying to answer a really specific question about, gosh, I have this place, I have this island, Roynamore, and I want to know exactly what happens here. And they're very valuable to do that, to try to replicate reality. But more importantly, they're a useful tool to explore the physics and the relative contribution of different variables. Because we can't go out in the ocean and say, well, I want to turn off all waves and just look at the effects of corals, or I want to take all the corals away and just test the effects of this. And that's what we can do with our models. And so why we want to do this is because, okay, Department of Defense gave us $3 million to study their facility. But we're the USGS. We're responsible for people everywhere. And so we want to take what we're learning in this one place and be able to look at other places without being able to invest all that money into it. So what we're looking at here is the effect of 2 things: how steep the fore reef is, and then how wide the reef flat is. And so what we see, and we're showing its impact on those short 5 to 25 second waves and those longer waves. As the reef flats get narrower, wave heights and run-up increases. Here in terms of fore reef slope, as the reefs get steeper and steeper up to about a 1 to 3, 1 to 2 slope, it increases, and then it actually decreases if you go to 1 to 1. That's probably because of a little bit of almost reflection. But this says if we're going to go look in other places, really the places that are most threatened are those with really narrow reefs and steep slopes. So again, this lets us go to other places on Bikini, Eniwetok, go to the Maldives, other places, and say, gosh, these are the areas which we really need to worry about. Now, we can also look at the climate change impacts. So one of the things is that corals impart roughness. They're a rough feature, and when waves propagate over them, they lose energy by frictional effects with that. Think about pulling like a carpet over rough rocks versus a smooth steel. It'll slide, there's less energy loss to friction. So here we're looking at the effect of hydrodynamic roughness. As we decrease hydrodynamic roughness, we cause increased wave heights, both those incident wave heights as infragravity wave heights and run-up. And so if we go from, say, this situation with lots of vibrant, good corals to a situation like this where there are none, it's going to cause increased wave heights and run-up. Also, just depending if wave heights increase, which is what we're not seeing in the Marshalls, but we see a lot of other places, if wave heights increase, we're going to get increased run-up. So the places we have to worry about are places where the reefs are getting smoother and wave heights are increasing. Okay, so now we have waves and we can figure out how much it runs up onto the island. How will it affect freshwater availability and thus habitability? This actually shows during the course of our 18 months of field observations, we actually sadly had a run-up event here in the Marshall Islands. Not big. These are the kind of waves we'd see probably 4 or 5 days a year. Just happen to hit during a spring tide, and you see the water rushing up over the island and running inland. This just shows one of the observational well fields that my colleague and co-PI actually installed as a master's student in 1990. So for those of you that do science, treat your students well, because they come back to help you down the road. And it's actually helping himself, but it was very fortuitous. It's actually one of the reasons why we're focusing here. So what we're showing here is a response to that March 2014 overwash event. And this shows, again, those waves washing up, and you see the water shooting across the road here. I'm showing you 3 things here. One is the red's the tide over a couple days. So the tide's going up and down, up and down, up and down. What we're showing here in the blue is the groundwater. Remember I said that fresh water floats on the salt water? So as the tide goes up and down, that fresh water goes up and down. What we see here, though, is all of a sudden the water level in the well, the fresh water, just jumped up. And that was because of this overwash event. What we see here in green is the conductivity, which is proportional salinity. So this is this overwash event. So the water level jumped up in the well because salt water piled on top of the island and started sinking in, and that chloride concentration, the conductivity and salinity jumped up. And you see the water level dropped down, all that water infiltrated in, but you don't see the salinity drop down right away. So remember, that takes that salt water time to work its way out. And how we had to figure out how long does it take for this to get back down to this level. So one of the ways we're doing that, well, we've made observations, and I'll show you some of the data for that in a sec, but we want to take it to the modeling realm. So here shows our grid of the island. So this is the North Shore. What you notice here is there's this feature here. It's this little topographic low, and you can see it a little bit in here. So now here's the model initiated with salt waters all around the ocean. The island's mostly freshwater. So using some of that data, looking at chloride concentration or salt through time, is you see how it decreases through time here. And so there, again, we have data to calibrate and validate the model. So now we can model that overwash event. So now we've kind of turned this sideways. Here's the north side of the island. So here we just inundated, we flooded just about the top, the northern, about 10% of the island, but that water got into this, topographic low and flowed inland. So here you see salt water sitting here. This is after 2 days after a overwash event. So what we see is we start to see recovery. So it's starting to rain, and that salt water, being more dense, starts to trickle down due to density effects through the island. Kind of looks like a lava lamp. But what we show here is it takes about 15 months for it to totally settle out, all the water to completely refreshen. So in this case, under existing rainfall it takes about 15 months of recovery. Now remember I said typhoons are going to decrease, so that's less rainfall. So that means that would probably take longer. So what we're trying to see is with sea level rise, when do those overwash events start happening more frequently than 15 months or maybe 1 month or 12 months? Because if there's storms, if we start to get overwashed once a year and it takes 15 months to refreshen, we have no fresh water. So what does this mean for the islands? So here shows, this is not an example for the Marshall Islands, and this is just kind of a schematic cartoon. This is based on real data up in the northwestern Hawaiian Islands, but this just shows an area inundated for different values of sea level rise. And so again, most of the islands are 2 to 3 meters high, so even with just sea level rise, maybe at 2 meters, you're still just kind of catching the outer lip of the island, maybe only inundating about 10%. And so here shows an example of that. I showed this earlier. However, if we start adding wave-driven flooding on top of that, that value goes up rapidly, non-linearly to be exact. So this is saying, gosh, you know, for the same value of sea level rise, we're going to have almost twice as much area flooded for that same value of sea level rise. So this is that same plot again. So what we can say here is, let's look at this, is basically we have the same amount covered by water annually at 1 meter sea level rise, if we include wave effects, that would have been the equivalent of 2 meters of sea level rise by itself. Or conversely, that same amount that it took 1.5 meters of just sea level rise, if we add wave-driven flooding on that, would happen at 0.5 meter sea level rise. We know, going back to this plot, we know that sea level is going to rise in the future. So what we can do is, instead of saying, let's start trying to put guesstimates of numbers of when this may happen. So these are just theoretical numbers. The first number is if sea level rise is a really slow rate, the other one's at a higher rate. But this says then, okay, so say, you know, we're estimating just with sea level rise alone, it may be 2,100 to 2,200 to reach this level. Well, now if we include waves, that's going to happen in maybe half or less of the time. So, you know, say if it takes 10% of the island to get overwashed and contaminate the lens, under just sea level rise conditions, say it's 2,100, now it's going to be 2060. Much sooner than projected before. And so again, this is Dickinson's numbers for just sea level rise, right? These are I just put theoretical numbers up here. These are his best estimates. So say 2050 to 2100. Say maybe that's 2070 on average around here, 2070 to 2080. This is just sea level rise. We add waves, and we're talking potentially half the time in the future. So this is what I'm talking about when we're trying to figure out those tipping points, when this is going to happen, because this is going to be almost a triage situation. We're going to start needing to talk about which islands are going to be impacted first, and thus people are not going to be, they're not going to be habitable. So okay, so our hope is, well, maybe these reefs aren't going to decay, they're going to keep growing and everything is going to be fine. At least that's our hope. And some of these places like Palmyra, which are not being allowed to fish and a lot of human impacts these days, maybe they will keep up. But the problem is I'm showing you some modeling done by Hoodink looking at the effects of temperature-driven bleaching. So we know the atmosphere is getting warmer. That's making the ocean warmer. Right now we're going to an El Nino condition where right now we're seeing a lot of coral or temperature-driven bleaching throughout a lot of the equatorial Pacific. This is showing you a map by time of where the bleaching is going to hit most of the islands. So in the equatorial Pacific, very soon, 2030s, 2040s, and then it's going to spread later and later to the poles as the ocean warms. So when corals bleach, they die. Now, if we look, the other thing is we're putting a lot of CO2 into the atmosphere. That gets into the ocean. It interacts in the ocean, and it forms carbonic acid. You've heard of the term ocean acidification. Well, ocean acidification is causing a massive, these are the percentage decreases in calcium carbonate accretion rates. However, this is declining greater from the poles towards the equator. And so the waters are more acidic at the poles, and they're marching towards the equator. The other thing about temperature, that was work by Van Dyzen. Temperature-driven disease outbreaks. When you increase the temperature, viral infections and things can increase. That will also increase from the poles outwards. So things aren't looking too good for coral reefs right now. As we talked about before, if we go from nice, healthy, vibrant corals to loss of corals, we lose hydrodynamic roughness, and thus we're going to increase wave heights, and we're going to increase wave-driven run-up. So where does that leave us? This is a true news headline. If it vanishes, is it still a nation? Now, I will argue that these islands are probably not going to vanish. As these reefs break down, they're going to generate sediment, and overwash will carry that sediment up onto the islands. However, you need water to carry seawater to carry sand up onto that island to make it grow vertically. So the only way you can build the islands is by inundating them. And usually it takes the biggest sediment deposit you can make by a flow is about 10% of the water depth. So every time a foot of water goes over the island, you only make 1/10 of a foot of sand. So the islands may grow, but they're not going to be habitable. And the argument people will make is, oh, the islands are going to grow. Well, yeah, you know what? New Orleans is going to be okay too, with floods and hurricanes over geologic timescales, but not on human timescales. However, what's happening? Well, these little island nations that don't make a lot of CO2 are really at the front lines. And they are actually putting lawsuits into the UN trying to get the industrialized nations, because these are the people who are going to lose their nations first. Hey, Florida Keys aren't going to do well, but you can drive a U-Haul to Jacksonville. Okay, so what have we learned? Typhoons will become less frequent, decreasing the wave forcing, but bringing less rainfall. These winter storm waves will decrease in height, decreasing the wave forcing. And sea level rise, however, the waves that are there, we're going to increase the depth-limited wave heights and thus run up. Climate change impacts, including increasing temperatures and ocean acidification, will also increase depth-limited wave heights by causing coral reefs to decay. So, again, understanding how the physics works, the conclusions, the trends, it appears that these islands will likely not have sustainable freshwater resources much sooner than once thought. And now we're talking about relocating island nations, some of which have existed for hundreds to thousands of years. And there's going to be obviously some geopolitical issues associated with that. So, as they say in the Marshalls, como tata, thank you very much. I'd like to take any questions.
Those of you who come every month, you know the drill. We have microphones in both side aisles. We would appreciate it if you would use the microphones to ask your questions, not only so that those in the room can hear you, but there are people watching the talk online, and so we want them to be able to hear you. If it's difficult to get to one of those microphones, just wave at me and I'll bring you one. So why don't we start over here with questions?
You mentioned that the height of the sea level rise varies throughout the Pacific Ocean. Why?
Over the recent past, I'll try to get back to that figure. Why that's happened recently is because of wind forcing. Pardon me, sorry, let me try to get back to that. You've heard of El Niños and La Niñas. Well, there's a larger cycle called the Pacific Decadal Oscillation, and we basically had a lot more La Niñas for about the past 20 years. During La Niñas, we get really strong trade winds blowing off the Americas into the Western Pacific. blow on your cup of coffee, you'll actually super elevate the water on the other side of the, or the coffee on the other side of the cup. That's basically what's happened. So what you see here is fascinating. Global sea level rise is going up about 3.5 millimeters per year. So what's happened is we push so much water because of this consistent period of La Niñas is it's piled up in the Western Pacific. We've actually had 0 sea level rise along California for the past 30 years. And it's basically gone up really strongly in the Western Pacific. Well, if global's doing this, first off, you can't keep doing this, right? It's going to snap. One of the things we've seen is these Pacific decadal oscillations going about 20-year cycles. Not saying that happens every 20 years, but a lot of people are starting to theorize, looking at the atmospheric forcing now, is that we may be at the end of this cycle, this cool phase of the PDO where we've had a lot more La Niñas. We may be going back in a time of more El Niños. So that means we may be doing this sometime soon. But again, global's still going up, and this is, again, 0.3 meters. We're looking, best estimates, 0.8 to 1.4 by the end of the century. People would say if you really take into account what's happening with ice, that might be 2 or more. Yes, sir?
I'm just wondering if there's any vertical movement of, these are extinct volcanoes basically, any vertical movement, uplift of any of these, any significance in any of these atolls?
Yes, sir. There's actually quite a difference. A lot of that, when I show those variations and how high the sea level high stand was, some of that is due to different uplift. The place where we're studying, Kwajalein Atoll and actually Majuro, both those sites in the Republic of the Marshall Islands, those are both relatively stable. What happens is as you're near wherever those volcanoes formed or a spreading center, it's usually uplift, and as the tectonic plates move away from there and cool, they cool and they sink. So as you get older, they're usually sinking. Right now, again, most of those are not. But that's how, like the northwestern, you look at the Hawaiian Islands, the new ones stick really far out. That plate, as it moves away from the hotspot, cools, and you get into these atolls, and then they're actually underwater geos and things like that. But yeah, there's a lot of variations. There's a lot of tectonic activity. I guess, here, it actually shows some of that. There's... by Fiji, there is the Tonga Trench, so there's some uplift in this area where Fiji's being uplifted, but most of these are an older, colder plate that is primarily subsiding. Is there some little local volcanism? Yes, but most of these, the Gilberts, the Marshalls, and the Carolines, most of those are stable, if not sinking, which is going the opposite direction of sea level rising.
And then not related to that, do you have any observations or opinions on where the Chinese are filling in the islands in the South China Sea?
And that was interesting. That got brought up at today's one. That's the Spratlys between kind of Vietnam, South China, Borneo, and the Philippines. Those are a bunch of atolls and island banks. And that is one solution. You can dredge a lot of sediment and put it up and build islands. No question about, we put people on the moon, we can build the Great Wall of China, we can engineer anything. We can engineer these islands. That's what they're engineering, the capital of the Maldives, the island of Mali. And they're building these massive concrete walls all around. Can we do that? Yes. There's thousands of atoll islets across Micronesia. Who's got the money to deal with that? Now, Department of Defense, they got deeper pockets than I do, and they will fortify their facilities. But the question is at what point, so some of these places, Kwajalein already they've already built at least a 3-foot high berm all around the island. They're starting to do that in Wake. The place we worked up here, Roy Namor, they're doing the same thing. But, then what about, what about, oh my gosh, wrong way. What about all these islands? And what about all the islands out here and all those other islands? You know, at what point is it more, you know, it's a cost-benefit analysis, and I'm not the one to make those decisions. It's these people. But are we going to engineer our way out? And the question is, do they have enough money to either make the islands higher, develop desalination facilities? But at some point, again, these folks fall under the U.S. Defense umbrella, and we have compacts with them. The people in the Gilberts, which is not under Office of Insular Affairs, they're overseen by the South Pacific Community, which is kind of EU funded. They're already starting to buy land in New Zealand. Yes, sir.
This is sort of in line with what you just said. Say in our U.S. controlled area out there, that our economic zone, an atoll goes under. Do we have to build that up in order to maintain our exclusivity in that commercial zone?
That's something that's being discussed both in Congress and the United Nations Law of the Sea. I do not know that answer. That's a lawyer's question to answer. I'm sorry. But it does bring up concerns, you know, because you lose one single island, you know, the exclusive economic zone's 200 nautical miles. I can't remember how many tens of thousands of square miles that generates of the exclusive economic zone. So the gentleman brought up the Spratlys. The Chinese are making their own islands to lay claim, which were underwater banks. So you can see how that is play out. And I'm guessing if push came to shove with that, I'm guessing if it really would cause the loss of exclusive economic zone, getting a dredger out there, I would have to believe someone would do that to not lose the large volume, but that's not my call. Yes, sir.
I apologize for getting here late, and I probably missed a lot of the fundamental parameters. But wasn't this caused by the fact that Edward Teller wanted to try out one of his new big bombs, and he made a mistake in his calculations, and the bomb was bigger than what he thought?
Well, that did happen. That was the Baker blast. And that did happen, and it piled stuff all over any we talk. And so that runnet cap, that big dome, most of it was from that Baker blast. But this is more sea levels rising because of climate change. You know, while the newspapers may talk about a debate, we know that atmospheric CO2 is increasing. It's basically causing a big, almost like a blanket over the atmosphere, is trapping more heat. Heat's increasing, ice is melting, and sea level is rising. We can debate whether the temperature is going up here or there, but every tide gauge, which is not on a gentleman, I can't remember who brought up, are the islands uplifting naturally, except those places where, like in Alaska, where the land's coming up because glaciers melted, like a boat. You step off a boat and the boat goes up. Every other place in the world that has not had ice-induced loss uplift, every one of those tide gauges shows sea levels rising. So we can debate, is it going to get hot in Oklahoma? Is it going to rain more here? Sea levels rising. And
Okay.
so...
Well, the next part of the question, what's the total population on all these islands right now?
Well, these atolls is about 100,000 in the Pacific. But we're not, okay, so I've talked a lot about atolls. The thing is a lot of the information we're finding on this about reefs and how they affect waves and run-up is that most of the high islands, I mean, Hawaii is a little different because they got big, broad volcanoes. You go to most other high islands in the Pacific, they've got very steep slopes and a very narrow little coastal plain where people live. And as sea level rise, it's going to increase inundation on those. If you add those in, that's those places with very limited coastal fringe. I think that adds another 10 million. Globally, coral reefs provide protective services for 200 million people around the globe. So about 2 years ago, the Asian Development Bank flew me out to Borneo for a meeting trying to look at reef restoration because they're pouring $100 million into reef restoration because they understand it protects a number of people in Southeast Asia and southern Asia. So we don't think about that much here, living in high California, but there's a lot of folks where these reefs provide critical protection.
And how would that guy Trump, does he have a plan for this? How would he deal with it?
I can neither confirm nor deny said plan, Senator. I'm just joking. I do not know, sir. Sorry.
Can I?
Yes, sir. Please go.
So we have lost a thermal homeostasis here.
I'm sorry?
We have lost a thermal homeostasis. There is a change.
Mm-hmm.
There is a new settings. Is this better or is this good? I know that if there is a perfect homeostasis, nothing change and nothing grow. So, besides the 100 million people that are around, and I understand, and there are economical situations, but in this planet, there has been an evolution because there have been changes.
Mm-hmm. Exactly. And you know what is, when we talk about impacts, it all from a frame of reference, right? Coastal erosion. Let's just talk about that. Along the beach. Coastal roads, no one lives there, it's not a problem. Sure, put someone's house in the way and then it becomes a problem. Right? The problem is right now we've got 7 billion people on this planet. 50% of them live within 50 miles of the coast. Get the majority of their protein from the coastline. And there's most all of our critical infrastructure, the majority of the U.S.'s critical infrastructure is less than 10 feet above sea level. So is it a problem that we're transitioning? If we weren't here, I'd say no. Problem is we are. And we built a lot of stuff real close to sea level. Most of all of our ports that carry something 70% of cargo across the globe, most of our power plants, most of our critical infrastructure, all of our naval bases. We built a lot of things in the way. So again, impact, I think, is a perspective thing. What may be a negative impact to one is a gain to another. Cockroaches might be really happy.
Yeah, and the dinosaur probably have the same issue.
Exactly, yes, sir.
Well, I want to thank Curt Storlazzi for an excellent talk, and thank all of you for joining us. And stay tuned to the news, and I hope to see you all back next month. Good night.
Thank you.